Good morning, everyone, and welcome to the fourth and unfortunately last day of the Chaos Communication Congress. The opening speech for today in this room will be automated botnet detection and mitigation. And we've got with us today Georg Wicharski, who has been doing some extensive research on, well, malware in general and has intensified his research to botnets. And he's going to give us some ideas of how to detect botnets, how to analyze them, and the most important part, how to get rid of them again. Enjoy.
Thanks. First of all, unfortunately, the day before yesterday evening, my laptop somehow disappeared here at the Congress, so I have to present a different set of slides I presented at Black Hat Asia this year, together with Thorsten Holz. So these slides are not the ones I wanted to present originally, but there's a high amount of slides who have the same context. So this talk is now called Catching Malware, but it's essentially the same content. First of all, what is our motivation to catch malware? Why do we want to track botnets, and why do we want to mitigate botnets? Then we'll have a look at our tools and techniques we currently have developed to learn more about botnets, which is first of all Nepenthes for malware collection, CW Sandbox for automatically analyzing the malware we've collected so far, and botsnipd finally for tracking the botnets we have found with Nepenthes and CW Sandbox. And then I'm going to present some results. So our motivation for botnet monitoring is we want to find new botnets, and botnets are a severe threat to today's internet community. Well, they are still a threat for several years now, but media attention has now come to botnets a lot more, so it's become a buzzword for most marketing people. And what is a botnet? Well, a bot spreads like worms. So this means they can not only by the nefarious purpose the botnet herder can have, they can take down machines, but simply by spreading like worms, they can already exhaust network resources and therefore take down a whole /16 in a time. So how do we get new botnets? Since it spreads like a worm, we can observe the infection and then take the bot that has infected our honeypot, analyze it, and then we obtain the information about the command and control server. And then we can track the botnet and eventually take it down. The typical communication flow for an ISC botnet is depicted here. I have no laser pointer, unfortunately. But you see here, we have a central, this is for an ISC botnet, a central ISC server, which doesn't have to run on a default ISC port. We have several bots, which are infected machines, which listen to the commands on the central ISC server. And we have an attacker, which is also often called the herder, who issues the commands in some whatever syntax that depends on the bot family to the botnet server, which then distributes it to the different bots. So how do we collect our malware? We have developed last year a low interaction honeypot daemon, which is a POSIX daemon, which is called Nepenthes. So with this daemon, we can automatically collect the malware, for example, like bots, but also normal worms which don't have a command and control infrastructure. And we do that by emulating known vulnerabilities. This is a severe limitation. We have to know the vulnerability which the bot is spreading with before we can actually catch the bot. This daemon is released under the GPL license, now available in version I guess 0.2.0 at nepenthes.mwcollect.org. So this daemon has a modular architecture because we realized as there's a lot of new vulnerabilities coming out each month, we need to have a simple way to extend the daemon. And we have separated the work which is to catch a single bot into different kinds of modules. First of all, there's vulnerability modules, which actually simulate the real vulnerability. Of course, then there's the payload and the vulnerability, which contains a shellcode. So we have shellcode handlers, which analyze the shellcode. Then we generate some generic URL from the shellcode, which doesn't have to be an HTTP URL. It can be any kind of URL. So we have download modules to actually download the malware from a central distribution server or from the attacking host. Depends on the bot again. And we have submission modules to take care of the downloaded malware and spread it in our collection servers or whatever. And additionally, we have an event system to automatically generically trigger events. And we have a shell emulation and virtual file system, as a lot of bots or malware for attacking relies on the Windows subsystem, like the Windows command shell. So this is a schematic overview. As you can see on the left, there's an Apprentice daemon core, which is the only executable file in the layout, so to speak, which opens the different ports and then associates them with the different vulnerability modules. Of course, there can be multiple vulnerabilities on one single port, so we have to do it in the core itself, so we have multiple modules per port eventually. Then we have the payload stage. The payload gets forwarded from the vulnerability module to the shellcode handling modules, which means since we have a generic interface, we can have any shellcode we know can come in over any vulnerability we know. So this means we can have a much higher coverage of shellcode vulnerability combinations. The shellcode modules rely on, analyzation modules rely on the Windows emulation, as there's often shellcodes which contain a tftp.exe command line simply or something like that. And then we have the URL of the malware generated, which is then getting forwarded to the download module to actually obtain the malware we've just learned about. And if we've downloaded the binary, we can submit it to the local file system with the submit file module, or submit it automatically to Norman Sandbox or to an XML RPC server, whatever suits you best for your personal setup. So looking at the modules in detail, first of all, the vulnerability modules, of course. As I've said, we have only an emulation of vulnerability services. And we don't simulate services to the whole extent like what a service supports. For example, there's the LSAS vulnerability in the Windows SMB implementation. And of course, we don't implement the whole Windows SMB subsystem, but we only implement of the daemons or services we emulate the amount we need to emulate. So we look at common public exploits, look what they require in functionality, and we only emulate that. So we have some kind of a finite state machine. So if an exploit expects a certain response, we give it that, but we don't have the whole service functionality. Currently, it's more than 20 available vulnerability modules, ranging from the old but still often exploited LDAS vulnerability to recent cyberattacks vulnerabilities, but that was even after this talk. So yeah, we always continue to develop more as some exploits are not exploited anymore and so on. So as I've said, we need to know the vulnerability in advance, and we need to manually analyze the vulnerability and the exploit for it, which is a lot of work. And we're now working on automation, which is not on these slides, unfortunately. So what we do is and we work with Corrado Leiter from the Institut Eurecom in France. He's working on software called ScriptGen, which can automatically, if deployed in front of high interaction honeypots, generate state machines of the exploits. Yeah, this is a bit difficult to explain without the slides, but you have a software running in front of the high interaction honeypot, then you can see different attacks coming from different hosts exploiting the same vulnerabilities, and using some genetic algorithms you can learn the vulnerabilities, so to speak. So we found a way to at least generate these state machines we have for the exploits automatically, and we're working on a setup to do this in real time on the internet with perhaps a delay of 2 or 3 hours. We can then catch even malware which is spreading through zero-day vulnerabilities. Yeah, here's an example of one of the oldest and traditional, so to speak, vulnerability modules. This is the LDAS exploit, which is one of the most exploited vulnerabilities even today because it's very reliable, and there's a lot of old boxes which don't have it patched even today, so it's often used still. And as you can see here, we just have the exploit here. It sends some data, some pre-generated requests, then receives some data, doesn't look at the received data at all, and then sends the next request. So for this simple case, our vulnerability module, which is not from the Apprentice but MW-collect D, the predecessor of the Apprentice, looks like this. no matter in which stage of the exploit we are currently, we just send some random garbage back to the host and at once into the next state, and this works with all known bots, because bots are like, most botnet herders, or a lot of botnet herders, are not too good at coding, so they take the public bot source, take a public exploit, somehow mod that exploit into their bot source, and you end up with such a cheap emulation which still works. Yeah, a brief overview about the vulnerability modules is we have one for the old DCOM and Altus vulnerabilities. As I've said, they are one of the most exploited ones. We also have ASN1 and WinS, which go to against the IIS server, and also some WinS is, of course, the hyped Windows 2000 vulnerability. These are also a lot exploited because they are more not against like client machines, but against Windows servers, and there's still a lot of Windows servers which don't have these vulnerabilities patched. Well, because if I say a lot, this means it's a really low percentage, but looking at how many computers are on the internet, it's still a relatively big absolute amount of computers. This is probably enough benefit for any botnet herder he wants. So they stick to these old exploits. And there's a lot of other exploit categories. For example, we have some other server exploits there, the MS-SQL exploits, and we also have, what is quite funny, some vulnerability modules which actually emulate backdoors or exploits in older malware. For example, if you look, there's Bagel and MyDoom, and both Bagel and MyDoom had a backdoor for the malware authors to upload new malware, but then other botnet kiddies found out how these bot backdoors work, and then they spread their bots on already infected computers via the backdoors of other malware. So we wrote these vulnerability modules to catch these as well. And we of course have the Veritas vulnerabilities and a lot of more. So once we've been attacked, we now obtained by cheaply emulating the server somehow the payload, which is in nearly all cases a shellcode. And we need a way to find out how, with this shellcode, the malware wants to infect the computer. So we have, first of all, most shellcodes have some restrictions, like there may be no 0 bytes or whatever. If you have ever dealt with shellcodes before, you're probably familiar with the principle of decoder headers. So what this is, you have a simple shellcode which is encrypted, and you have a very short assembler code in front of the actual shellcode which decrypts or decodes, or however you want to name it, the actual shellcode with some simple XOR or whatever. So we have some generic XOR patterns. This is actually PCRE patterns we're using for that, which detect which encoder is being used, extract the key, and then we can de-XOR them ourselves. And then in a second stage, so to speak, actually we loop endlessly here more or less to a certain extent you can configure. So you can have a decoder which decodes a decoder, which decodes a decoder, and so on. But anyway, in a certain stage then there comes the actual code which would then download the malware on a real machine. So there's some, for example, some generic create process shellcodes or signatures we have which match most create process shellcodes. We have signatures which may just generically match an URL, because once we've decoded the shellcode, sometimes there's just an HTTP or FTP URL in plain text in the shellcode, which at some point gets pushed or whatever on the stack, and we can just match against it, and we have already the URL with not too much work. And the same goes for some generic commands like tftp.exe, ftp.exe, which are used. We can grab these in plain text as well and then use. So this is an example of one of the bots using a command shell code. First of all, it just uses a bind shell. Oh no, this one has a commands embedded. That's clear. So this one just invokes the create process API on Windows using the following parameter. It's just one parameter. So it echoes a control file for ftp.exe into a temporary file called II, and then invokes ftp.exe with some parameters, like you see -s means it shall use the file it created before as a command file, then deletes the command file, and then invokes the downloaded file, which is called svchost.exe. So we take all this information, run it through our Windows shell emulation, and what we get at the end is this URL. So we have a command sequence and we generate a URL from it, simply by emulating all the echo calls and having an ftp.exe command file interpreter, and then we can generate a URL from it and then pass this one onto the download modules to actually download this FTP URL. What you see here is rather nice. We came across this using the ASN exploit, and what you see here, the actual payload, or in the top you see first an HTTP request and then a MIME encoded payload. So we had to also include our own MIME decoder, or base64, I guess it is, the algorithm used or similar. And then again, after MIME decoding, you see the command line at the top, what we did with the original hexstam. We could again generate a command sequence from it. It's using, so this is also a create process shellcode. And then turn this into a TFTP URL. So we have a lot of download modules for all these different kinds of URLs. And as you can see here, using the Windows shell is pretty common, but it's not only used with the create process API and shellcodes. The most poor thing most bots do is they take a public bind shell shellcode, so because most proof of concept shellcodes are bind shells or reverse shells, and they don't change the shellcode in the public exploit because that would be too professional. They cannot do that, they're too lame. So what they do is they take these default bind shell shellcodes and add code to their bot, which then connects into the shell and automatically sends the commands they want to it. So this is really cheap and poor, but it's the way it works for them. So usually you don't see just one exploit going over your network, but you see an exploit and then an automated shell connection, and they just retry for several times connecting into the shell before they drop that host, and then send some Windows commands via this bind shell list as well. No real black hat would do that, but most botnet herders are kiddies still today, even though media tells you, well, it's a lot of high capital behind botnets nowadays and whatever. So now we have that nice URL, and we can now somehow obtain the malware using our download modules. We had to implement our own HTTP and TFTP modules because we first stuck with curl because we were CURL, the library. We thought we were developing open source, so why don't rely on other open source software as well? The problem is the CURL library is RFC compliant, and bots or malware is not RFC compliant. That means we had to implement our own download modules, which, well, it looks like HTTP, but there's certain flaws in some malware, like they don't send a carrier to return at the end of each line, but only a return or whatever. And this means we had to write a very, very friendly download module which accepts a lot of bullshit, and we had to add some tweaks. The same goes for FTP, because the FTP client, the ftp.exe in Windows, is also not RFC compliant. And then, because the FTP client in Windows is not RFC compliant, malware authors wrote their FTP servers not RFC compliant, so the Windows FTP client could load it from their servers, but then again we could not use CURL because URL was RFC compliant and it couldn't work with these intentionally broken FTP servers. And then of course there's a lot of, well, let's say proprietary download modules like csend and creceive, which were very famous in Agobot. This is not a real download protocol. You just connect to that port, send or receive the length of the file you want or are getting, and then the file is simply streamed over that connection, so nothing so sophisticated. And we have the very, very sexy download link module, which downloads the malware from link bots, which is really nice because the link bot download is three-staged. First of all, you have a shellcode. Then in the shellcode, the shellcode is automatically generated in runtime by the link bot, and it generates a code that is then executed, which in turn generates a key. This key is used for authentication at the malware. So in order to download the malware, you have to see what key the shellcode generates, and then use this key for authentication at the actual exploiting host for being allowed to download. Linkbot appeared like, I don't know exactly, it appeared some month ago after the first Nepenthes release, so we were somehow tempted to assume this was a try to avoid Nepenthes, but we were able to write some even more generic patterns, so to speak, which could then, with some C code, also extract the keys from the shellcodes. And now a link.bat URL at the end, for example, contains the base64 encoded key used to download the malware, which is generated in these shellcode steps. Yeah, that's it about the most nice servers. No. Well, as I've said, this is not my laptop, and it's coming back. Just a second, please. Yeah, by the way, if anybody saw it, it's a C-base, a black bag with a yellow arrow on it. That's mine, and I would like to have it back. Yeah, I guess this computer is now turned off for whatever reason. Anybody familiar with Dell laptops? Ah, it's coming back. Huh? No, it has like 2 hours of battery remaining. Battery is critically low. Okay. Just try to give it some power. Well, yeah, there's a reason why I try to never present about my own laptop. Well, if any of the heralds could help me, that would be nice. I've never used a Dell laptop before. Weißt du, wo man hier Strom einsteckt?
It's super useful if you combine it with I talked about earlier. You can get into that no page. You might be able to do a lot of allocations page right after. So if you'd have a function pointer that said null, it would go to your no page, which has all these nulls with sure.
Yeah, it's resuming now.
The entire no page will just be off, right?
Yeah, I'm sorry, but it's coming back now.
And you'll have your shellcode in there, right? And so these things sometimes help in exploiting no-pointed references. There are constraints. Sometimes this is enough. Right. So the last piece of no-pointed references. Some operating systems also map to a page by default, but they don't allow you to read it or write it.
Well, is there any special key combination I have to press to? Ah, there it is. Great. So here we go again. Yeah, these are the most sexy download modules we have there, and we can download nearly all malware with these download modules now. So the next step, of course, is then somehow handling the malware, because we're not like people collecting stamps. We don't collect malware just for fun. So the simplest thing is for doing it like simple collection is write it to the hard disk, but we have some submission modules for submission into various databases, which is great for correlating data and whatever. There's a submission module which automatically extends the malware to the normal sandbox. You configure your email address in the submission module, and so you automatically get email the sandbox to run of this. Now CW Sandbox also has a public interface, and in cooperation with cwsandbox.org, there's also the same module also works with CW Sandbox. And there's the submit Gotik protocol, which submits the file via the Gotik protocol, which I'm going to come back later to. Yeah, in theory, we would now have an Apprentice demo, but this is a Windows laptop, so unfortunately I cannot show you the software, but you have a screenshot there. So what you see is the log output, and what you can see up there is that there's several exploitation attempts using an already black hole DNS distribution server. So they were using a central server, fdp.peruvianpower.com, for spreading, but even at that time when we were running this test, the DNS was already black hole to that fictional IP address, so these runs failed, and as you see, it's the same with the limateam.com server. Yeah, and then there were some unknown shellcodes. We have, well, this is like only a probe whether the computer is vulnerable. As you can see, it was a 0-byte shellcode. Yeah, and then what you can also see there is that, well, the timeouts were reached for these black hole hosts, and what is interesting there is also there was another computer, 84.60.251.5, which was like a normal home computer, which was infected, which was serving as a malware server. In that case, we often assume that this one was simply behind a normal personal home router, and well, of course, these are using NAT, so we couldn't connect back to the spreading host to download the malware because we couldn't get through the home router's NAT. NAT, network address translation, you're probably familiar with it. And yeah, that's it, what you can see on the screenshot. It's the same again down there. So sorry, no demo here. So what we have found is now that the MW collect lines, well, you simply have a lot of MW collect sensors, which is now, of course, Nepenthes. The software is now called Nepenthes. And we have a central database. And I mean, the picture is not too interesting. But so we have now a database of over, I guess it was 27,000 different malware binaries collected through the last, yeah, it's nearly a year now. And we're sharing them with everybody for free because, you know, it's all in the spirit of open source. And if you want to get access to the binaries, you can just go to that URL down there and apply. Of course, we have some joint requirements. First of all, because we want our database to grow, you need to supply your own sensor for access. So everybody who contributes malware also gets all the other malware. And the second thing is you need to somehow prove some level of trust because, of course, we don't want to feed all these black hats with the malware. Yeah, that's it about the MW Collect Alliance. So if you have any questions to this, feel free to come to me afterwards. There's a lot of people already. I guess it's more than 100 sensors now distributed over the whole world. And yeah, we're also submitting all malware for free to all these antivirus vendors. So it's just doing a good thing on the internet, and it's not hard to set up an Nepenthes daemon, so it would be great if you could join us. Now to the second part. We have now, with some work, obtained our malware binary. And yeah, of course, as these are often packed and whatever, you cannot just run them through strings and then see some IRC command and control server information. But we need to analyze the collected binaries somehow. And this work, CW Sandbox, is written by Carsten Willems as part of his diploma thesis, hence the name CW. I guess it was at the university, I guess it was still Aachen, at the University of Aachen, but they now moved to Mannheim. Yeah, so what the sandbox does is an automatic behavior analysis of the malware. So we take a VMware or whatever VM, install Windows in it, install the sandbox software, and then tell the sandbox software to run the binary. It works similar to Norman Sandbox regarding the output, but the main difference is that Norman Sandbox has its own virtual machine included in the software, whereas you run CW Sandbox in an existing Windows virtual machine. And yeah, there's currently still a better version available, but they are also already selling it. So it's a commercial software, but most researchers get access for free. It's, I guess, available from Sunbolt. You can, but you see it's an .org domain. First, there's a free open web interface, so you only need to pay if you want it on your own site. If you don't have any privacy issues with running it at their sandboxes, you can get the results for free. And also, if you're a researcher, yeah, you can talk to Thorsten Holz. He's not today here anymore, but he was yesterday, or just drop in an email. It's also on that page, and there shouldn't be any problems. So how does it work? Yeah, how does a Windows program work? You have just a normal Windows application at the top layer, which uses the Windows API, or perhaps if it does as it shouldn't, it also already calls the native API. And this Windows API is just some libraries providing some chain calls, either going directly to the kernel or via some other API going to the kernel. And there you have the user-made kernel mode barrier, which is going via interrupt or sysenter, depending on your CPU and Windows version. And then at the end, you somewhere land in the Windows kernel where your request actually gets processed. So as you probably know, Windows is a really monolithic kernel, so everything is running in kernel space, all the real stuff. So all you have in these Windows API is either simply a wrapper, so the API is consistent between kernel versions, or does sometimes some pre-processing, like the new Windows XP and whatever kernels are all highly depending on Unicode. They're all using UTF-16, and if you have a normal ASCII command called, it's of course first converted to UTF-16 and then sent to the Windows kernel. So this is the way a normal Windows program works. Now, this is a simple example of code hooking. No, this is not an example of code hooking yet. This is how it looks then if you have a real call. You have a create file function in the application, which opens a file or creates a new file. Then in the kernel, in the user mode kernel wrapper, you have the jump in point for the API, which, as I've already explained, then first converts it to Unicode, and then calls create file W, which is the Unicode version of create file, which then calls ntdll zw create file, which means this is a native API, so to speak, which shouldn't be used as it's not consistent between different Windows versions. And in TDLL, you then have the setup of your jump to a kernel space. You set up some structures, path information, and then call the interrupt, or call this enter, depending on, as I've said, Windows and kernel, Windows and CPU version. And then in NTOS kernel, actually, you have the software interrupt handler, which then has a really big table, which has a list of all the calls, and then does the actual work in step 4. And then, of course, you go all the chain back to the application. Now, how does CW Sandbox actually hook these codes? It's a very simple method called inline code overwriting. Normally, you have your normal jump create file hook. But what it does, it first executes that function, and then after executing the function, no, sorry, I'm wrong here. It jumps to the hooked code, which is overwritten. This jump gets overwritten by their code. Then there's a custom hook code, like, I want to preprocess this code, I want to log it or whatever, and then jumps to the saved stub. So what the stub, which is actually where the jump was, is saved somewhere else, and it then jumps there. And then in the saved stub, there's a setup to the actual call, which is happening there. And then it's actually calling the kernel in the end. So you just take the original code, put it somewhere else, take a jump to your code there. After that, jump to the original code, hoping that it's position independent, and then continue execution as normally. So by API code hooking, code overwriting, and DLL injection, because all that overwriting takes place in a DLL, which is getting injected into the malware process, you can hook all the codes of these API calls and then record them. And by doing that, you can, of course, seeing all kind of APIs for file access or whatever access. And you can record that information. And what I do with CW Sandbox is do that for 3 minutes, and then you have a huge list of just which functions were called with which parameters. They analyze it and convert it to XML, which is not so easy as it sounds, because you just have handle values and need to actually convert them to which files were accessed when, and you need to correlate time and whatever. But in the end, you get a nice fancy XML output, what has it done, and you can then further use it. So you have that CW Sandbox process in the virtual machine, which invokes the malware application or executes it, and forcefully injects the CW monitor DLL, which is doing the actual hooking into that process. That DLL is communicating by some pipe with the CW Sandbox. The CW Sandbox is doing the actual recording. And since we're doing code hooking here, we can also behave like a userland rootkit. So CW Sandbox can hide its own presence as it filters all APIs which could be used for detecting CW Sandbox presence. And also, since we are hooking all code, we can also hook the code to execute new files. And if the malware application, for instance, downloads a new binary and then executes it, we can also inject the CW monitor DLL automatically in the new binary. Nowadays, you often have downloaders just spread you have a really small binary, which is executed, downloads the real huge malware from the internet, and then execute that one. And this is really neat because you're seeing both depths, because there's no real command and control or whatever in the downloader. It's just fetching the file and executing it. But this way you see both files. Yeah, that would be a demo now here, but on Black Hat, which I don't have here. Sorry. As I've said, not my slides for this Congress. And now, what we have achieved now is We know where the botnet command and control server is. We know how to communicate with that server. And now we want to see what's going on, which commands are issued actually, and so on and so on. We have some properties of botnets that we can use for us. First of all, a botnet cannot impose authentication that is not also encoded in the bot's binary. Why is that? If you would have some sort of authentication and you wouldn't have it in the bot, how would the bot join the botnet? I mean, the bot, if there's a password, the password must be somewhere in the bot. If there's some specific encryption key, it must be in the bot, whatever. So by looking at the bot's binary, we can obtain all information necessary to join the botnet. Then, usually, and we rely on that, commands are forwarded to all bots and not some selected single bots. So what this means is that if we're seeing what one bot is seeing, we're probably seeing what all bots are seeing. So we might not see some commands to some specific bots, but from our experience, and we've now been working on botnets since 3 years, there is seldomly commands issued to specific bots. So we assume we're seeing everything that is there. And then botnets are so large that there either isn't any replies of bots at all, because if you issue a single command and all your 1 million bots you have in your great big botnet would then report back whether the command was successful, you would be simply DDoSing yourself. So there's no channel back because you cannot do that. Botnets are usually too big to actually get any responses. And if they are still so small because they are just by some script kiddies or whatever, if there is like 5,000 bots, there's a high chance that at least 50 of these are just experiencing a ping timeout or are not, normal Windows user which just plugs out the power, so they are not logged off the botnet and still there but not responding. And what this means is we don't need to respond to valid commands. We just try to appear as a silent turned off bot, and so we can hide in the masses. So this means we can just join the botnet, listen to all commands, and log it, and that's it, without being detected, hopefully and probably. So how do we impersonate such a bot? The simplest method is just run the bot binary in CW sandbox or in the honeypot or whatever, put a sniffer on the outside of this box at the network border, and just look at the traffic, what's happening. And this has some problems. First of all, if you are running the real bot software and somebody is issuing a DDoS command, you're pretty fucked up because you're participating in the DDoS, and there's a lot of legal implications. You can avoid that by clever rate limiting and whatever, but it's a lot of work you could just avoid. The second problem is what if the command and control goes over SSL? Then you need to write your own SSL code, so you have to do a man in the middle, and that's just a lot of work if you just do it from the outside. So it's the most realistic because it replies to the commands as it should, and it does what the herder expects, but it's also hard to use. So better we use just some existing software for the control protocol. Still today, a lot of botnets are IRC based, so IRC is a command and control protocol, and there's a lot of good IRC clients out there we could use. The problem there is, at some point it becomes really hard if you're having an IRC and tracking. Like at times we were tracking 500 different botnets at a time, and you have an IRC with 500 open windows. Then either you have a big, huge list on paper which window in IRC is what botnet, or you're just lost because with 500 tabs you cannot distinguish which server are you on, and it's just not usable. So even better is you implement your own generic bot emulation software, and we've done that. It's called botsnoopd because we sniff on botnets, and it's a daemon. So what does it do? What does it do? It's a daemon dedicated to snoop different kinds of botnets. Like, as I've said, we have a lot of IRC botnets still today, but emerging is HTTP for command and control, so you have an HTTP server which is serving the commands, and they're continually fetching the file with the commands. And also what has been there already is peer-to-peer, so not file sharing, but peer-to-peer communication. So there's a really decentralized command and control protocol, like in the Nugashi botnet, which is interestingly not so hyped by the media because there's still about 200,000 hosts in that peer-to-peer botnet. But the problem is, since there has not been so much research on it, nobody knows how to take care of that peer-to-peer botnet because there's no central server you can take out, as we'll see later. And so, well, we live with that this botnet is still floating around and people just don't talk about it. So again, we realized that there might be a lot of need for extending this daemon, so we have again chosen a modular design, which is extensible via plugins or libraries. And we have developed our own daemon, since we're using all the network stuff in Apprentice and shared in botnet for performance. So we're single-threaded using Paul and whatever, which is really fast. So we can have, we have at least 100 botnets on a single machine, but that single machine isn't one of our spare hardware. It's an 8 megahertz Duron with 256 megabytes of RAM. So with a good server, you can track more, but we haven't tried this. And yeah, it will be released under GPL when we're really confident with it. At the moment, well, it's stable, but not as stable as it could be, probably. So it's still in the work. A schematic overview is the most important thing is the client modules. We have one for client for ISC, one for HTTP, one for Nugasha. And these are just the implementations of the command and control protocol. So client ISC is just a simple ISC client, HTTP is a HTTP client, and Nugashi is a bit of more advanced because if you want to participate in a peer-to-peer network, for command and control, you cannot just connect to the central server and assume you're getting all commands, but you need to really participate in the peer-to-peer botnet. So you need to contact a node, and this one tells you, no, I'm full, please try these ones. And then you contact these, and then at some point you connect it to some amount of nodes, and then getting, hopefully, all these commands. Of course, there can be separated clusters of nodes with no connection in them. It's a usual properties of a peer-to-peer network, so it was a bit more work. Yeah, then we have added to that proxy modules you see on the left. So we have our networking core, which again transparently uses proxies because what we experienced in the past. There is some botnets where they find out that you're not a valid bot. Like for example, there's some botnets which just have 80 bots. And you think that's really small, and well, we don't care anyway, but these 80 bots are some really high bandwidth servers, so they might have the same bandwidth as an usual 5,000 botnet, but if you're having only 80 bots, it's really obvious if somebody pops in, doesn't reply to the commands, and so the pre-assumption with hiding in the masses does not work. So what we saw was there was a huge DDoS against us, and luckily we were on the dial-up IP, so we just dialed back in, and some other poor guy was then DDoS dialing in after us, but well, that wasn't our problem. So we've added proxy modules for SOCSphere or HTTP proxies, and now we have several volunteers who also have dial-up IPs, so we can spread on different IPs, and we don't need to dial in all the time. And we're not using public proxies because that would be really bad. You know, you would be seeing a lot of DDoS against public proxies if you would be using them otherwise. And you can go with SOCS4, you of course can go through the Tor network as well. Then we have emulation modules, which are invoked by the client modules, because we were not confident that we were kicked off that 80 bot botnet, so we added our emulation of generic IRC bots. Like if it says there's some, for example, in our bot there's .auth for authentication, and we then look at the first 5 results to that attempt, and either then say, okay, this key was okay or not, depending on what the others answer. So we don't need to hide in the masses at all anymore. And the other thing, the generic IRC, no, that was the RBOT one, but the generic IRC one reacts on commands like .j or .join, so we can join other channels on an IRC server, for example, if there are additional commands in other channels. We have added reaction modules. The SnortSum module, SnortSum is a project for distribution of snort rules or no, not rules, like firewall blocking rules. So by adding this reaction module, we could then take the IPs of the participating bots, give them to the SwordSam project, and then they could at all participating firewalls just block all these bot IPs. So this has two implications. First of all, if you're getting DDoS and already blocking all bot IPs anyway, it's more the upstream provider which gets DDoS and not yourself anymore. And the other thing is there is some internet sites which are using this who have rather large traffic, and users of infected computers cannot access these internet sites anymore because they're firewalled from them, and that makes them feel like my computer is broken, I need to find someone who repairs it, so hopefully the machine gets somehow disinfected. The ASN mail reaction module just sends a mail to the ASN of the command and control server, so we run an whois on the IP and try to find some abuse information or whatever, and also mail neighboring ASNs, so we hope that this way the command and control server gets somehow taken down. Yeah, of course, now that we are all tracking these commands, we also want to log them. We log them to files into our own IRC control network, or also into a Postgres database, which again allows for great correlation. And yeah, this is a brief schematic overview of this little piece of software. I'm sorry I don't have a demo available again because it's not my laptop. But how do we now mitigate botnets? This is the shortest part of the presentation because it's one of the least researched parts. The simple thing is we changed the DNS entry of the command and control server to some other IP address, like loopback. But this has three problems. First of all, we need to convince the DNS provider that this is a bad thing, and there's huge amounts of DNS providers in Russia and China who say they pay, I don't care what they do. The second thing is it has to rely on DNS anyway. If it's using static IP lists or even a peer-to-peer botnet, this cannot harm the botnet at all. Yeah, these were 2 in 1. So if it's peer-to-peer, it doesn't work because it's not centralized, and if it's not using DNS, it doesn't work because, yeah, well, obviously. Then what we can do for us, if we don't have contact to a DNS provider or whatever, we could, if we're a university or whatever, we could block all traffic to the command and control IPs to at least protect the students at our university. And the most, or the best approach is just take down the C&C server. So we try to contact some law enforcement agencies in the countries of the C&C servers. Well, there's not only DNS providers, but also server providers in Russia and Romania especially. And law enforcement in Romania doesn't seem to care too much. Perhaps it changes after they joined the European Union, but I doubt. So we need the cooperation of these people, and they say, botnets, what is that? Or botnets, yeah, well, but they are attacking your country, why should we care? Or they say whatever. So this is hard to do. And all these three have the problem. If it's a peer-to-peer botnet, there's no central instance we can take out. Yeah, so these will probably fail as well. So what's our conclusions? Yeah, our honeypot-based techniques can help us to learn more about botnets and autonomous spreading malware, so we can collect it. Then we have to analyze the malware, and then we can efficiently find new botnets without having the need to have an infected computer at our own network. And so we can do local and global mitigation. But we need more research, we need more time, and we need more help, of course, because we want the zero-day vulnerability support, and we want more people just like tracking botnets who are willing to spend their free time on contacting law enforcement agencies. Although the Shadow Server organization, which can be found at shadowserver.org, is doing a pretty good job on this. Yeah, and of course, the more sensors for malware we have, the more malware we have to analyze, the more botnets we can find. So if you would join the MW Collect Alliance, that would be really helpful. Yeah, and that's it. Got any questions? Yeah, that either means my presentation was really bad or really good, so no questions. one question.
So more and more malware is starting to detect virtual machines. I mean VMware and virtual PC and stuff like this. And how do you analyze this kind of malware? Because I think it will be a very big problem in the future because...
Yeah, this is now, it's getting more and more. So the question was, if I understood it right, how do we detect malware, or how do we analyze malware which detects the presence of a virtual machine? Well, the most simple answer is we have one physical machine dedicated for this, which is using a hardware restore PCI card, which restores the hardware on each reboot. But this is slow because we need to reboot the physical machine. So if we... and this one needs to be activated manually, so it's not in the automated process. But as we see the threat emerging, that because it's more and more just packers which already include the detection mechanism, we are currently working on writing our own virtual machine as well, which already includes the analyzation software, which also has some other implications, as we don't need to run the whole operating system anymore, just the malware in this virtual machine. But as you might know, writing a virtual machine is not such an easy step, so this is part of ongoing research. I'm also doing this for my company and not as open source, so I cannot talk too much about it. But if you can feel free to come to me later if you want to know more about this. So yes, it's a great problem that they are adding VMware detection, but we also have QEMU, and I've not ever seen a single piece of malware which is running QEMU detection. The backside again is QEMU is slower than VMware, and well, this is the thing which is just emergent, and we first have to see how hard it would impact our research. Any other questions?
Should you be helped by the new KVM in the Linux kernel with QEMU, because it's really fast now, because it uses the new virtualization in the AMD and Intel processors?
Yeah, it's not, well, so the question was on this QEMU, right?
No, there is KVM.
Okay.
It's in the latest kernel, and there are models for the older kernels, and it's a virtualization, and it uses a forked version of QEMU for using Windows on it.
Yeah, that might be another thing we should look at. So it's called KVM?
Ja, KVM, also V auf Deutsch.
Klar, okay, Dankeschön. Well, if there's no more questions, thanks for your time, and I'm also open for questions now in private here.